What happens to a star after its fire goes quiet? Not in a sudden explosion, not in a blaze of cosmic violence, but in a slow, silent transformation into one of the strangest objects in the universe, a white dwarf. These small stellar remnants can hold the mass of a star in a space roughly the size of a planet, glowing only with leftover heat while quantum physics quietly keeps gravity from winning. Before we begin, thank you for spending your time here and letting this calm journey into space be part of your day or night. If this kind of relaxing science storytelling helps you unwind, please like the video, subscribe to the channel, and share it with someone who enjoys peaceful cosmic mysteries. And if you feel like joining in, leave a comment telling us what time it is where you are and where you're listening from. Now, let us drift gently into the silent mysteries of white dwarf stars. White dwarfs begin as an ending that is not quite an absence. After a low-mass star has spent the long central part of its life turning lighter elements into heavier ones, the balance that held it steady begins to loosen. The star does not vanish. It changes form. Its outer layers swell outward, drift away, and spread into the surrounding space as faint enriched gas, leaving behind the exposed core that once worked quietly at the center. That remaining core is the white dwarf, small enough to be planetary in size, dense enough to belong to a much stranger class of matter, and calm enough in appearance that its true nature is easy to underestimate. It is not a star in the old sense. Because the steady furnace of fusion has ended, it is not a planet either, because ordinary chemical bonds cannot explain how it holds itself together. It is a stellar remnant, a quiet leftover of a life that has already passed through its brightest chapters. And yet it remains one of the most important objects in the future history of the universe. Most stars are not massive enough to become black holes. Many are not massive enough to leave neutron stars behind. The more common fate is gentler in shape, though not in physics. A star like the Sun, after burning through its main supply of hydrogen and passing through later, unstable phases, does not have the mass required for a final catastrophic collapse into the deepest kind of darkness. Instead, it releases much of itself. What remains is a compact core, rich in the products of stellar evolution, no longer able to maintain the pressure of active fusion, but still hot from the energy stored inside it. This is why a white dwarf can shine even after its nuclear engine has shut down. It is glowing because it is cooling. Its light is not a sign of new power being made, but of old heat slowly escaping. The distinction is quiet, but it changes everything about what the object is. A living star shines because it continuously produces energy at its center. A white dwarf shines because it once did. The path into this state depends on the mass and history of the original star. In many ordinary low-mass stars, the exposed remnant is made mostly of carbon and oxygen, the ash of helium fusion. In smaller or interrupted cases, other compositions are possible. Some may retain helium-rich cores, while the heaviest white dwarfs may contain more oxygen and neon. These differences matter to specialists because the interior ingredients help shape cooling, crystallization, and possible later instability. Yet across these variations, the basic identity remains. A white dwarf is the leftover core of a star that has reached the end of ordinary fusion and survived as something compact, hot, and supported by a pressure unlike the pressure in everyday matter. It is a dead star only if death is allowed to include structure, memory, and long physical consequence. It still keeps the record of what happened inside the star before the outer layers departed. Its mass, temperature, atmosphere, and slow fading all preserve traces of the earlier life. In this sense, a white dwarf is less like an extinguished lamp than a warm coal beneath ash, not burning in the same way anymore, but still carrying the history of fire. From a distance, the word white can make the object sound simple, almost decorative, as though it were merely a pale point of light. The reality is more layered. White dwarfs are born extremely hot, often with surfaces far hotter than the sun, and their early light can fall in the blue-white part of the spectrum. Over immense spans of time, they cool through different colours, becoming fainter and redder before fading beyond easy visibility. Their name reflects how many of the first known examples appeared, not a permanent state for every one of them. Even this naming history carries a small lesson in observation. Astronomical objects are often named from the first clues available, and later understanding has to grow around imperfect language. A white dwarf is white only for part of its cooling life. It is dwarf only in size, not in density or importance, inside it. Matter has been pushed into a state far beyond anything familiar on the surface of Earth. The quietness of the remnant is therefore misleading. It is not quiet because little is happening. It is quiet because the deepest work has become internal, slow, and hard to see directly. The formation of such an object also marks a change in how a star belongs to its surroundings. During its active life, a low-mass star is a continuous source of light, heat, wind, and magnetic activity. It shapes planets, warms atmospheres, drives chemistry, and holds its system in a stable gravitational arrangement. Near the end, as it expands and sheds its outer layers, it can transform that system profoundly. Nearby planets may be engulfed or scorched. More distant bodies may be disturbed as mass loss changes the gravitational balance. Dust, gas, and rocky debris can later fall onto the compact remnant, leaving traces in the white dwarf atmosphere. These traces sometimes reveal the remains of former planetary systems. Because heavy elements should sink quickly in the strong gravity of a white dwarf, if they are still observed near the surface, they may point to recent or continuing accretion from shattered asteroids, moons, or planets. In this way, some white dwarfs become quiet archives of worlds that no longer exist in their earlier form. They do not simply mark the death of a star, they can also preserve evidence of the unsettled aftermath around it. The scale of a white dwarf invites a careful kind of wonder. Something with a mass comparable to that of a star can be compressed into a volume comparable to that of a planet. The usual habits of size no longer work. In ordinary experience, as more mass tends to mean more bulk. In a white dwarf, the relationship becomes far less intuitive, and the reason for that inversion will matter later. For now, the important point is that the object is small enough for its surface gravity to be enormous. Light leaving it can be subtly shifted by the gravitational field. Material falling onto it can be accelerated violently. A thin atmosphere, sometimes made mostly of hydrogen or helium, sits above an interior where the normal architecture of atoms has been overwhelmed. The visible surface gives only the slightest suggestion of the compression beneath. Telescopes receive the light, measure its colour, separate it into spectral lines, and infer temperature and composition from distant signals. What appears as a faint dot is therefore translated into a physical story, not by seeing the interior directly, but by reading the clues that escape from its surface. This is one reason white dwarfs are so useful to astronomy. They are not only remnants, they are clocks. Because they no longer generate significant energy by fusion, their cooling can be modelled as a slow release of stored heat. A young white dwarf is hot and bright. An old one is cooler and dimmer. By studying populations of white dwarfs in star clusters or in the wider galaxy, astronomers can estimate ages and trace histories. The method is not simple, because mass, composition, atmosphere, crystallization, and surrounding environment all influence the pace of cooling. Still, the principle remains powerful. A white dwarf carries time in its fading light. It marks not the rapid drama of explosion, but the patient accounting of energy leaving matter. This makes white dwarfs especially suited to calm attention. They are extreme, yet they are not usually violent. They are dense, strange, and ruled by quantum behavior, yet their visible evolution unfolds slowly enough to become a measure of galactic age. They sit at the meeting point between stellar history and deep future, between bright life and long cooling. Their importance grows from that position. They show what happens when a star has no fuel left to spend, but too much mass to become ordinary matter again. They also show that the universe does not end its stories cleanly. A star can finish shining by fusion and still remain physically rich for billions of years. A core can be exposed, compressed, and cooling, yet still hold back collapse by means that require a different layer of nature to explain. The first mystery of the white dwarf, then, is not only that it exists after a star has died. The deeper mystery is that it remains stable at all. Once the outer layers are gone and the nuclear fire is over, gravity should seem to have the final claim. Yet these remnants persist, faint and compact, suspended between collapse and cooling by a form of pressure that does not come from heat, light, or chemical bonds. The dead star remains, and its stillness becomes the doorway into stranger physics. The future population of white dwarfs begins with a quiet fact about the present sky. Most stars are small. The bright stars that draw attention across the night, the blue giants, the swollen red supergiants, the rare massive stars that end in spectacular collapse, are not the usual form of starlight. They are the visible exceptions, powerful because they spend their fuel quickly and announce themselves across great distances. The more common stars are modest, cool, and faint. Red dwarfs, in particular, make up the largest share of stars in the Milky Way, and because they burn their hydrogen so slowly, many of them will remain active for spans of time that dwarf the current age of the universe. They do not dominate the eye, but they dominate the count. That difference matters for the long story of white dwarfs, because the universe is not only shaped by the objects that shine most brightly now, it is also shaped by the objects that will remain when brightness has thinned into endurance. A white dwarf is not rare because the path to making one is exotic. It is common because the path belongs to ordinary stars, the ones too small to collapse into black holes and too light to leave neutron stars behind. A galaxy filled with low-mass stars is therefore a galaxy preparing, over very long intervals, to fill itself with stellar embers. Not all of those embers have arrived yet. Many stars that will eventually become white dwarfs are still in the middle of their lives, quietly turning hydrogen into helium in their cores or shells, preserving a balance that can last for billions or even trillions of years depending on mass. The current white dwarf population comes from stars that were massive enough to age more quickly, while still ending below the threshold for more violent remnants. These stars have already passed through their red giant phases, already released outer layers, already exposed compact cores. They are the early representatives of a much larger inheritance. In young regions of star formation, white dwarfs are scarce because there has not been enough time for most stars to reach that state. In older stellar populations, they become more visible as accumulated remnants, marking the long history of previous generations. Each one is a small endpoint, but together they form a census of elapsed stellar time. The galaxy keeps them the way a forest keeps fallen seeds and old roots, not as the most visible feature, but as part of the deeper counting of what has lived there. This slow accumulation changes the emotional scale of white dwarfs. They're not merely isolated curiosities. They are a forecast. Every star below the right upper mass range that completes its ordinary evolution without being disrupted, is moving towards some version of this compact state. The Sun itself is on that path, though not soon in human terms. Long after its stable main sequence life ends, after it expands and loses its outer atmosphere, the remaining core will cool as a white dwarf. That future does not belong only to the solar system. It is a general pattern repeated across the galaxy, with variations written by mass, composition, companions, and environment. Some white dwarfs will be alone, drifting quietly after the loss of their outer layers. Others will remain in binary systems, orbiting another star and perhaps drawing matter from it. Some will be surrounded by debris from disrupted planetary material. Some may become part of more unstable histories, especially if their mass grows toward a critical boundary. But the underlying population grows because ordinary stars continue to age. The universe builds white dwarfs not through rarity, but through patience. What makes this especially striking is that the stars most responsible for the future have not yet delivered their final remnants. The smallest red dwarfs burn so slowly that none has had time, since the beginning of the universe, to complete a full life and become a white dwarf. Their future evolution remains a matter of models rather than observation, because the cosmos is still too young to show the ending of its longest-lived stars. That fact gives white dwarfs a strange dual role. They are observed objects, measured and catalogued in the present, but they are also incomplete representatives of what the stellar future will become. The white dwarfs seen now are mostly the remains of stars that aged faster than the smallest ones, stars whose lives were long but not immeasurably so. The faint red majority has barely begun to reveal its final chapter. Far ahead, when fresh star formation declines and the brightest massive stars have long since disappeared, the universe will be increasingly populated by remnants white dwarfs, neutron stars, black holes, and the slowly cooling remains of smaller stellar lives. Among those remnants, white dwarfs are expected to be immensely numerous, because they are the common end of common stars. The silence in the phrase white dwarf is therefore misleading in a second way. A single remnant can look lonely, but as a population, white dwarfs are a major part of galactic evolution. They influence how astronomers estimate ages, how they read the history of star formation, and how they understand the fate of planetary systems. In dense stellar environments, they contribute to the mass and dynamics of old clusters. In binary systems, they can shape dramatic outcomes when matter flows from a companion or when two compact remnants orbit close enough to merge. Some of the most important explosions in astronomy are connected to white dwarfs that are pushed beyond stable conditions. Yet most white dwarfs do not announce themselves that way. Most simply cool. They become fainter year after year, century after century, beyond the ability of ordinary time to notice. Their importance does not come only from rare catastrophes, but from persistence. They are the quiet background into which much of stellar history gradually settles. The galaxy, then, can be understood as a place where light is being transformed into memory. Active stars pour energy outward while their cores rearrange matter. When the fuel pathways narrow and end, the remnant keeps the result. A white dwarf is the dense memory of nuclear burning, not in a conscious sense, but in its composition and structure. Carbon and oxygen inside many of them testify to earlier helium fusion. Surface layers of hydrogen or helium reveal the last light elements left above the dense interior. Heavy elements in some atmospheres can suggest the recent fall of rocky debris. The object is small, but it gathers several histories at once: the life of the parent star, the changing orbit of any surrounding planets, the age of the stellar population to which it belongs, and the physical laws that prevent it from shrinking without limit. When many white dwarfs are studied together, these histories become statistical rather than personal. Their temperatures and brightnesses form distributions. Their masses cluster around common values while preserving outliers. Their cooling sequence in a star cluster marks a faint boundary where the oldest remnants have dimmed below detection. In that boundary lies a clock, and in that clock lies a way to measure how long the cluster has been aging. There is also a future darkness implied by this population, though it does not need to be treated as bleak. A white dwarf cools because there is no strong internal source replacing the energy it loses. The process is slow at first and slower still as the remnant fades. Eventually, after times far longer than the present age of the universe, a white dwarf should become a black dwarf, a cold, dark remnant no longer glowing with visible warmth. No black dwarfs are expected to exist yet, because the universe has not been old enough for white dwarfs to cool that completely. This means every observed white dwarf is still, in a sense, young compared with the full length of its possible cooling life. Even the faintest ones known are not final fossils of stellar heat, only advanced embers. The future black dwarf stage remains theoretical because time has not yet produced examples. That absence is useful. It reminds the study of white dwarfs that astronomy often sees not the whole story, but the portion the universe has had time to write. The present is not a complete sample of all possible endings. It is a middle chapter viewed from inside the process. This long view gives the white dwarf population a special calmness. They are not rushing. They are not burning through fuel. They are not held up by the outward force of new light from fusion. They are waiting in a physical sense, cooling through the ages while gravity presses inward and quantum pressure answers from within. Their numbers will grow as more stars leave the main sequence and shed their outer layers. Their temperatures will spread across a wider range as old remnants fade and new ones are born hot. The galaxy will carry both fresh white dwarfs and ancient ones, bright blue-white points and nearly invisible red cooling relics, all connected by the same underlying path. The bright sky is temporary in its present form, but the remnant sky is cumulative. Every ordinary stellar life that reaches this endpoint adds another quiet object to the ledger. The mystery is not whether the universe can make white dwarfs. It plainly can. The deeper question is how such dense remnants can exist in such numbers without collapsing further, and why the most common stellar endings depend on a pressure that ordinary experience never reveals. White dwarfs bring the problem of balance into its simplest and strangest form. In an ordinary star, gravity is always trying to win. Every layer pulls on every other layer, and the whole mass presses inward toward the center. A star remains extended only because something inside it answers that inward pull. During the long active life of a star, the answer comes from heat and radiation generated by fusion. Nuclei combine in the core, energy moves outward, and the pressure produced by hot gas and light helps hold the star against its own weight. The balance is not stillness in the ordinary sense. It is a steady contest, a condition called hydrostatic equilibrium, where inward gravity and outward pressure match closely enough for the star to keep a stable shape. A white dwarf appears after that familiar contest has changed. Fusion has ended in any normal lasting sense. The outer layers have been released. The exposed core remains. But the engine that once supplied outward pressure is no longer working as it did before. This creates the first serious difficulty. The remnant is too massive to behave like a planet, but it lacks the central fire that supports a living star. It should seem trapped between two categories, with neither of their usual supports available. Planets and moons do not need fusion to keep their shapes, because their matter remains mostly ordinary. Atoms and molecules hold each other at fixed distances through electromagnetic forces. Solids resist compression because electron clouds repel. Crystal structures push back, and chemical bonds make matter difficult to squeeze. Even rock and iron, under great pressure, retain enough atomic structure to keep a planet from simply falling into itself. Gravity may round a planet, heat its interior, and separate its materials by density, but it does not usually erase atoms across the whole object. In a normal planet, matter still belongs to the world of chemistry. It can be melted, fractured, layered, and compressed. Yet its resistance comes from the electromagnetic structure of atoms. A white dwarf has crossed beyond that comfortable regime. Its mass is stellar, concentrated into a radius comparable to Earth. The gravity at its surface and through its interior is too strong for ordinary atomic spacing to survive in the familiar way. It is not merely a heavy planet. It is the leftover core of a star, pressed so tightly that matter has to find another way to resist. The other familiar support, the support of a shining star, is also gone. A living star is not held up by chemical bonds. It is far too hot and massive for that. Its atoms are stripped into plasma, a fluid of nuclei and electrons, and the pressure comes from heat, motion, and radiation flowing outward from fusion. This pressure is renewed as long as the core can keep releasing energy at a rate that balances the gravitational load above it. When that balance changes, the star changes with it. Cores contract, outer layers expand. New burning shells may appear for a time. The star passes through unstable late phases because the balance has become more complicated and less durable. When the white dwarf is finally exposed, the earlier system of support has ended. The remaining object can still be hot, but heat alone is not enough to explain its stability. If ordinary thermal pressure were the main defense, then cooling would steadily weaken the remnant in a dangerous way. As heat escaped into space, the white dwarf would be expected to shrink further, perhaps catastrophically. Yet observed white dwarfs do not collapse simply because they cool. Some are hot and young, some are cooler and ancient. Across that range, they remain compact objects with recognizable structure. Their continued existence says that another kind of pressure is present, one that does not depend mainly on temperature. That is the key to why white dwarfs feel so quiet and so radical at the same time. Their surfaces fade, but the support beneath does not fade in the same ordinary way. Before that deeper support is named, the scale of the problem deserves careful attention. A white dwarf can contain a large fraction of the Sun's mass inside a sphere roughly the size of Earth. This means the average density is enormous, far beyond metals, gemstones, or any material known from daily life. A small spoonful of white dwarf matter, if it could somehow be brought intact into ordinary conditions, would represent an immense amount of mass. The comparison is useful only as a signpost, because white dwarf matter cannot simply be handled like a dense mineral. It exists under the pressure of the star itself. Remove that pressure, and the state of matter would not remain the same. Still. The comparison shows how far the remnant has moved from ordinary substance. In such an object, the question is not why gravity matters. The question is why gravity has not already finished the collapse. This was one of the great conceptual puzzles of compact stars. Once the fuel is gone, why is there a remnant at all? Why is the core not pulled inward until it becomes smaller and smaller without limit? The answer cannot be found by imagining matter as tiny hard grains pressed together. At the densities of a white dwarf, that picture breaks down. Atoms overlap. Electrons are no longer attached in the usual way to individual nuclei. The matter becomes a dense sea of charged particles, with nuclei embedded in a shared population of electrons. The interior is not ordinary atoms stacked more closely than usual. It is a different physical arrangement, forced into existence by gravity. The remnant takes the ashes of stellar burning and compresses them until chemistry no longer provides the important answer. The support has to come from quantum mechanics, from the behavior of particles under confinement. That shift matters because it changes what pressure means. In a gas on Earth, pressure usually comes from particles moving because they have heat. Warm the gas, and the particles move faster. Cool it, and the pressure drops. Inside a white dwarf, there is still heat, especially when the remnant is young. But the essential resistance is not just thermal motion. The electrons have been confined into an extremely small volume for the amount of matter present. They cannot all settle into the same lowest state. Nature forbids that crowding at the quantum level. The full explanation belongs to the later movement of the script, but its consequence can already be felt here. Even a cooling white dwarf contains an internal pressure arising from the allowed arrangements of its electrons. Gravity presses inward, but the electron population cannot be compressed without being forced into higher states of momentum. The more the star is squeezed, the stronger this resistance becomes, at least up to a boundary. The balance problem is therefore not solved by adding another familiar force to the list. It is solved by entering a less familiar layer of matter. The white dwarf is stable because the inward pull of gravity is met by a pressure that comes from quantum exclusion, not from burning fuel. This makes it different from both planets and normal stars. A planet resists collapse because its atoms and bonds still matter. A living star resists collapse because heat and radiation from fusion keep the gas extended. A white dwarf resists collapse because its electrons are pressed into a dense quantum arrangement that refuses further crowding in a particular way. The object is cold in its future, but not helpless. It is dead in the sense of no longer sustaining normal fusion, but not physically simple. Its stability is not a leftover habit from its active life. It is a new balance, reached after the old one failed. The star's luminous life ends, but gravity does not get a clean victory. Instead, the collapse is arrested by a rule that belongs to the smallest scales of nature. A whole stellar remnant, visible across interstellar distances, depends on the behavior of electrons, particles so small that they cannot be pictured as little spheres in any honest way. The large and the small meet without ceremony. A mass like a star becomes stable because microscopic particles obey a rule of identity and state occupancy. This is why white dwarfs are not simply astronomical objects. They are bridges between gravity and quantum mechanics, between the architecture of galaxies and the hidden order of matter. Their existence shows that the fate of a star can be decided not only by how much fuel it has or how brightly it once shone, but by what matter is permitted to do when pushed near the edge of ordinary form. The balance is not unlimited. That limitation will become important later, because a white dwarf can be stable only below a certain mass. Add too much matter, and the pressure that once answered gravity begins to change character. The electrons are driven to more extreme motion, and the remnant approaches a boundary where the white dwarf state can no longer continue. For now, though, the essential point is more restrained. The compact corpse remains because collapse has been paused by a pressure that does not need ongoing fusion. The star has stopped burning, but it has not surrendered its structure. In that pause lies the central mystery of the white dwarf, a dead stellar core, too dense for chemistry, too inactive for ordinary starlight support, held open by a law that belongs to the quiet depth of matter itself. The light of a white dwarf can make the remnant seem more alive than it is. It shines, sometimes with a clean blue-white intensity when it is young, and that brightness can suggest continuity with the star that came before it. Yet the meaning of the light has changed. In an active star, light is part of an ongoing engine. Energy is being made in the core as nuclear fusion joins small nuclei into larger ones, and that energy moves outward through the star, helping maintain the pressure that resists gravity. In a white dwarf, the core no longer sustains that kind of steady fusion. The glow is not new power rising from a central furnace. It is stored heat leaking away. The remnant shines because it was once hot enough to shine, and because matter so densely packed cannot lose its warmth all at once. Its light is the slow departure of energy left behind by earlier stellar life. That distinction separates a white dwarf from the star it used to be. The same photons that make it visible cannot be treated as the same kind of support that once held the original star open. Radiation pressure is real, and light does carry momentum. When photons move through matter, scatter from particles, or are absorbed and re-emitted, they can push. In the cores of luminous stars, where temperatures are extreme and energy production is continuous, that pressure can become an important part of the balance against gravity. In the most massive stars, radiation pressure can be especially significant because their interiors are so bright and their fusion rates so intense that light itself becomes a major structural force. But a white dwarf is not being fed by such a central supply. Its light is thermal emission from a hot compact body cooling into space. The radiation carries energy outward, but it does not replace what leaves. It is not a self-renewing support. It is a loss. Each escaping photon makes the remnant slightly cooler than it would otherwise have been, and over long times the glow weakens. If radiation pressure were the essential reason a white dwarf remained stable, then cooling would be a slow structural danger. The fading of light would mean the fading of support. The remnant would move toward collapse as its brightness declined. Observations do not show that simple path. Hot white dwarfs and cool white dwarfs can both remain white dwarfs, held at roughly planetary size by a support that does not disappear merely because the surface becomes dimmer. That is why the visible glow must be interpreted carefully. It is evidence of heat, age, and atmosphere. It is not the main answer to the balance problem. A young white dwarf begins with enormous surface temperature because it is the exposed core of a former star. The outer layers have been stripped away or expelled, leaving behind dense material that has not yet had time to cool, at first. The remnant can be very bright for its size, but its size is small, so the total luminosity is far below that of the earlier active star. A small hot surface can shine fiercely per unit area, while still releasing much less energy overall than a broad star powered by fusion. This creates a subtle contrast. The surface may be hotter than the sun's surface, while the object as a whole is far less luminous than the sun. Temperature and total light are not the same thing. The white dwarf is a small ember with a high heat at its skin, not a large fire continually remade from within. Its brightness is therefore a sign of compactness as much as heat. The remnant has a limited reservoir of thermal energy, and the only ordinary direction for that energy is outward. The atmosphere, often dominated by hydrogen or helium, regulates how the heat escapes. Different surface compositions can change the pace of cooling because they affect opacity, the degree to which material blocks or permits radiation to move through it. A hydrogen-rich layer can insulate differently from a helium-rich one. Magnetic fields, crystallization in the deep interior, and the composition of the core can all influence the cooling history. These details matter because white dwarfs are used as cosmic clocks. Their light fades in a pattern that can be modelled, though never without careful attention to the physics beneath the surface. The fading itself is not a simple dimming of a lamp. It is the visible expression of heat diffusing through matter under extreme compression, passing through thin outer layers and escaping into interstellar space. Over billions of years, the remnant cools. It moves along a cooling sequence from hot and blue-white toward cooler, redder, fainter states. Far beyond the present age of the universe, the expectation is that white dwarfs will eventually become black dwarfs, dark remnants that have lost the heat needed to glow visibly. No such object should exist yet, because the universe is too young for even the oldest white dwarfs to complete that descent into darkness. This absence makes every observed white dwarf a halfway thing, even when it is ancient by ordinary measures. It has already passed beyond stellar fusion, but it has not yet reached thermal silence. It shines from the middle of an immense cooling process. The light that reaches telescopes is therefore both a clue and a reminder of limitation. It shows the surface condition now, while pointing back to a hotter birth and forward to a colder future. The glow belongs to time, not to ongoing burning. This is why the language of death can be both useful and misleading. A white dwarf is dead as a normal star, but it is not inert. Heat flows, atmospheres settle, heavy elements sink under intense gravity unless new material falls in. Cores may crystallize as ions arrange themselves into more ordered structures, while electrons continue to provide pressure. Some white dwarfs pulse slightly in brightness, their interiors ringing in ways that allow astronomers to study hidden structure through a field called asteroseismology. None of this restores fusion as the central source of power. Instead, these processes reveal that cooling remnants have internal lives of a different kind. Their evolution is slow, physical, and often quiet, but not empty. The fading light is part of that continuing evolution. It carries information from the outer layers and sometimes from deeper changes, but it does not provide the fundamental pressure that prevents collapse. That pressure must be something with a different relation to temperature. The need for such a pressure becomes clearer when the energy of radiation is considered. Fusion in an active stellar core produces particles and photons associated with very high energies. And through many interactions, the energy is redistributed before finally emerging as lower energy light from the surface. The interior remains hot because fusion keeps feeding it. A white dwarf has no comparable long-term source in its center. Its photons are ordinary thermal radiation from cooling matter. They can still be abundant, especially when the remnant is young, but their outward pressure is not enough to carry the weight of a stellar mass compressed into a planetary volume. Gravity is too strong, and the light is not being renewed at the required rate. The object is shining as it empties a thermal reservoir, not as it maintains a furnace. The difference is not cosmetic. It decides the structure. Radiation pressure depends on light that is intense enough and trapped enough to matter dynamically. In a white dwarf, the deeper resistance comes from the state of the electrons, not from the brightness of the surface. The glow may make the remnant visible, but visibility is not stability. This quiet separation between shining and support is one of the most important turns in understanding white dwarfs. In everyday thought, light and life are easily linked. A star shines because it lives as a star. A dead object is expected to go dark. White dwarfs refuse that simple division. They are dead in one sense and luminous in another. They are no longer ordinary stars, yet they still radiate. They are cooling, yet they do not collapse as cooling proceeds. The glow invites attention, but then it points away from itself, toward the deeper matter beneath it. The light is not the answer. It is the fading veil over the answer. As the remnant loses heat across immense time, its ability to remain a white dwarf must come from something that does not require the constant creation of new photons. That something has to be built into the compressed matter itself, into the way electrons behave when gravity crowds them so tightly that atomic boundaries can no longer remain meaningful. The surface can cool, the color can change, the luminosity can fall almost beyond detection. Still, the remnant can persist, because the true support is not the dying light, but the quantum structure hidden below it. Once that distinction is made, the next movement becomes unavoidable. The white dwarf has to be entered not as a glowing point in space, but as matter under compression, where atoms lose their familiar outlines and the interior becomes stranger than the light escaping from it. Matter under compression does not become strange all at once. It passes out of familiarity by degrees, first losing the structures that make ordinary substances recognizable, then losing the boundaries that allow atoms to behave as separate little systems. In a white dwarf, the pressures are so high that the old language of solids, liquids, and gases becomes only partly useful. The remnant may have layers, temperature gradients, a surface, and an atmosphere, but its interior is not a lump of ordinary material packed more tightly than usual. It is the ash of a star forced into a state where gravity has taken away most of chemistry's freedom. The nuclei remain, often carbon and oxygen in many common white dwarfs, but the electrons no longer belong comfortably to one nucleus or another. They are not arranged like the electron clouds of ordinary atoms, where each atom keeps a recognizable identity and chemical behavior emerges from outer shells. Instead, the electrons spread through the compressed interior, shared across the object in a dense collective sea. That sea is where the next answer begins, because once matter is squeezed into this form, pressure is no longer only a question of heat. The white dwarf's interior is built from loss, but also from a new kind of order. Molecules are gone first. The delicate arrangements that make water, rock, air, or organic matter meaningful cannot survive the temperatures and pressures involved. A molecule depends on electrons being shared between atoms in structured ways, and those patterns require a scale of space that white dwarf matter does not grant. Push harder, and even atoms lose their usual individuality. The nuclei remain as heavy centers of positive charge, but their surrounding electrons are forced into a common population. In ordinary matter, the size of an atom is mostly the size of its electron cloud. The nucleus is tiny by comparison. Remove the freedom of those clouds. Press them until they overlap everywhere, and the matter changes character. The star becomes a place where atomic identity is blurred from within. Carbon is still carbon because its nuclei carry the charge and mass of carbon nuclei, and oxygen is still oxygen in the same nuclear sense. But the chemical personality of those elements is largely absent. Chemistry has been replaced by dense plasma physics and quantum mechanics. This is why white dwarf matter can be described as degenerate. Though the word can sound misleading outside physics, it does not mean spoiled or chaotic in the ordinary sense. It means that many available states of the system have collapsed into a special kind of arrangement, with particles packed into the lowest allowed quantum states until the rules of nature force some of them higher. The term belongs to the mathematics of identical particles, but its physical meaning can be approached gently. The electrons are not free to do anything at all. They are constrained by confinement, by their identity as electrons, and by the rule that prevents too many of them from occupying the same quantum state. The full importance of that rule will come next, but in the interior itself the consequence is already visible in structure. The electrons form a pressure-bearing sea, while the heavier nuclei contribute most of the mass. The nuclei are sluggish by comparison, carrying the weight, while the electrons carry much of the resistance to being squeezed. That separation of roles is one of the white dwarf's defining features. Gravity acts on the whole remnant, but the response comes strongly from the electrons because they are light, numerous, and forced into shared quantum conditions. The nuclei may arrange themselves in ways that depend on temperature and composition, and in older white dwarfs they may gradually crystallize. Crystallization here does not mean the formation of an ordinary diamond-like object in the popular sense. It means that the charged nuclei can settle into an ordered lattice as the interior cools, while the electrons remain spread through the structure as a conducting background. The phrase giant diamond is tempting, because many white dwarfs contain carbon, and because dense carbon can form crystals under certain conditions. but it oversimplifies what the remnant is. A white dwarf is not a gemstone drifting in space. It is an object where carbon, oxygen, helium, hydrogen, and other ingredients may exist in different layers and states, all governed by gravity, temperature, electric charge, and quantum pressure. Some of its interior can become more ordered as it cools, releasing latent heat and slowing the fading of the remnant. That process adds another layer to the idea of white dwarfs as cosmic clocks. Their cooling is not merely the steady draining of warmth. It is shaped by phase changes inside matter that can no longer be understood as ordinary substance. The outer atmosphere gives little hint of this interior transformation. At the surface, the gravity is so strong that elements tend to separate by mass. Lighter hydrogen can float above helium, and heavier elements tend to sink quickly unless fresh material falls in from outside. This creates deceptively simple spectra for many white dwarfs, because the visible layer may be dominated by only one or two light elements, even while the interior is mostly carbon and oxygen. The surface is a thin mask over a compressed core. When astronomers see heavy elements in some white dwarf atmospheres, those elements often become evidence of recent pollution from planetary debris, not a direct window into the deep interior. The interior has to be inferred through mass, radius, temperature, cooling behavior, pulsations, and theory. It is known through indirect methods, and that indirectness gives the object part of its quiet scientific power. The white dwarf does not reveal its dense matter plainly. It lets small clues escape, and those clues have to be assembled into a picture of matter under pressure. Inside the remnant, the ordinary scale of emptiness has been reduced. Atoms in familiar matter are mostly open space, at least in the sense that the nucleus occupies only a tiny part of the atom's volume. That statement can be misleading if imagined too literally, because electrons are quantum objects rather than little planets orbiting a centre. Still, it points toward a useful contrast. Ordinary matter has room for electron clouds to define size and behaviour. White dwarf matter has lost much of that room. Nuclei are packed far more closely, and the electrons are pushed into conditions where their allowed motions define the pressure. The material is not nuclear matter, because the nuclei have not merged into a continuous mass of neutrons and protons. That more extreme state belongs to neutron stars. A white dwarf remains less compressed than that. But far beyond ordinary atomic matter, it sits in the middle regime, after chemistry has failed but before nuclear densities are reached. This middle position is part of what makes it so instructive. It shows that there are stages of collapse, and each stage asks a different piece of physics to answer gravity. The word pressure itself becomes deeper here. In everyday life, pressure often feels like a push from particles bouncing around because they are warm. In a white dwarf, temperature still matters, especially near the surface and in young remnants. But the essential support does not vanish when the matter cools. Even if the electrons were taken toward very low thermal energy, they would not all fall quietly into the same simplest condition. Their confinement would still force a distribution of momenta. In that sense, the compressed matter contains a pressure rooted in the allowed structure of quantum states. It is not a mechanical spring, not a burning furnace, and not a chemical scaffold. It is a resistance created by what identical electrons are permitted to be when crowded together. Gravity makes the star small, but the crowding makes further compression costly. The more tightly the electrons are confined, the more their momentum are spread upward, and that produces the outward response that keeps the remnant from shrinking freely. This hidden interior gives the white dwarf a peculiar calm. It may look like a point of cooling light, yet beneath that light is a system where most familiar categories have been stripped away. Matter has become simpler in one sense, reduced to nuclei and a sea of electrons, but also more profound. because its behavior is controlled by rules that are rarely noticeable in ordinary experience. The former star has stopped producing energy by fusion, but its collapse has exposed a different kind of lawfulness. The white dwarf is not held up by the strength of material in the human sense. It is held up by the structure of possibility. Electrons cannot be arranged just any way gravity demands. Their allowed states form an invisible architecture, and the remnant rests on that architecture as surely as a planet rests on rock or a living star rests on heat. The next step is to name the rule behind that architecture. It is a quiet rule, often introduced in atoms, where it explains why electrons fill orbitals in ordered patterns. In a white dwarf, the same rule expands until it supports something star-sized. Matter under compression has carried the story inward, from fading light to crushed atoms to a shared electron sea. What remains is to understand why that sea refuses to become infinitely still. The Pauli exclusion principle begins as a rule about small things, but in a white dwarf it becomes large enough to hold up the remains of a star. It says, in simple form, that identical fermions cannot occupy the same quantum state at the same time. Electrons are fermions, and that makes the rule unavoidable wherever many electrons are crowded together. In ordinary atoms, the principle helps explain why electrons fill shells and orbitals instead of all dropping into the lowest available arrangement. The rule gives atoms their layered structure, gives chemistry much of its shape, and helps matter resist being pressed too closely in everyday conditions. In a white dwarf, the same rule is carried far beyond the scale of an atom. The electrons are no longer neatly assigned to separate nuclei, but they remain electrons, identical in the deep quantum sense, and they still cannot be placed carelessly into the same state. Gravity may squeeze the remnant with the weight of a star, but it cannot command those electrons to ignore what they are. That is the beginning of electron degeneracy pressure, the quiet pressure that appears when electrons have been confined so tightly that the lower energy states are already occupied. The word pressure can make the process sound like heat, as if the electrons are only pushing outward because they are warm. But degeneracy pressure is different. It can exist even when thermal motion is not the main actor. It comes from the structure of allowed states. Each electron in the crowded interior must have a place in the quantum arrangement, and when the simplest places are filled, additional electrons must occupy states with higher momentum. Momentum here means a particle's quantity of motion, not necessarily motion along a visible path. Electrons do not behave like tiny beads flying through a container in a perfectly classical way. Yet the mathematical result has a physical consequence. Confinement raises the range of momenta that electrons must possess. Higher momentum states create a resistance to further compression. The star is not being held up by little electrons deciding to push back. It is held up because the compressed electron sea cannot be arranged into a smaller space without changing the allowed distribution of those states. The Pauli barrier is therefore not a wall in the material sense. It is a limit built into possibility. This distinction matters because it explains why cooling does not remove the support. In a normal hot gas, pressure falls as temperature falls, because the particles move more slowly. In a white dwarf, the electrons responsible for the main support have already been forced into a degenerate arrangement. Their pressure is linked more strongly to density than to temperature. Squeeze the star more tightly, and the electrons are confined more severely. The available low momentum states are occupied, and the remaining electrons must fill higher ones. That raises the degeneracy pressure. The remnant settles into a balance where gravity pulls inward, and the electron sea resists being confined further. The balance is not gentle in its ingredients, but its outcome can be stable for enormous spans of time. A white dwarf can fade, cool, and grow dimmer while the deeper electron support continues. The surface loses heat into space, but the central quantum rule remains. This is why white dwarfs can become old without simply collapsing as their light weakens. Their visible glow is temporary. Their quantum support is tied to density and identity. The principle also explains why white dwarf matter is not simply compressed ordinary matter. In ordinary matter, electrons are already governed by exclusion, but there is enough room for the familiar architecture of atoms and molecules. Their states form shells around nuclei, bonds between atoms, and the detailed structures of chemistry. Under white dwarf conditions, gravity has reduced the available volume so much that these separate arrangements overlap. The electron states belong to the whole dense system. The star becomes, in a careful sense, one vast quantum object, not because it is delicate or mystical, but because the electrons must be described collectively. The positive nuclei provide most of the mass and charge balance. The electrons provide the pressure that keeps the remnant from continuing inward. The ordinary picture of matter as small pieces stacked together gives way to an interior where the important question is how many electron states are available at each momentum and how completely those states have been filled. The pressure comes from counting possibilities, and the count is enforced by nature with perfect consistency. The role of spin adds a small but important detail. Each electron has an intrinsic quantum property called spin, which is not quite ordinary rotation, even though the name suggests it. Because of this property, a single spatial and momentum state can hold electrons only in a limited way. In the simplest atomic language, an orbital can hold two electrons with opposite spin orientations. In the dense interior of a white dwarf, the same underlying restriction persists in a more continuous sea of states. Once those allowed placements are filled, the next electrons have to occupy states that correspond to greater momentum. The result is not optional. It is not a matter of the electrons repelling each other electrically, though electric forces also shape the plasma. Even if the electrical picture were softened in the dense background, the exclusion rule would still impose its own kind of resistance. The electrons are crowded, and because they are identical fermions, crowding them further demands that some occupy more energetic conditions. That demand appears macroscopically as pressure. This is one of the most beautiful reversals in the physics of white dwarfs. The star has lost the elaborate complexity of its earlier life. It no longer has burning shells making new energy in the old way. It no longer has a broad luminous envelope swelling and breathing across space. It has been stripped down to a dense core, and yet that stripping reveals a more fundamental structure. The remnant survives because matter has rules deeper than temperature. The same exclusion principle that gives the periodic table its layered order becomes, at stellar density, a support mechanism for a dead star. In a laboratory, the rule is inferred through spectra, chemical behavior, and the organization of atoms. In the galaxy, it announces itself through the existence of compact remnants that should otherwise seem impossible. A white dwarf is a visible proof that quantum mechanics is not confined to microscopic laboratories. It is written across faint points of light, across the cooling cores of stars, across objects heavy enough to bend surrounding motion and small enough to be mistaken for something simple. The pressure has limits, and that fact keeps the story from becoming too neat. Degeneracy pressure strengthens as the white dwarf is compressed, but the relationship changes as the electrons are driven to higher and higher momenti. At lower densities, the electrons can be treated without strong relativistic corrections, and the pressure rises steeply enough to support more mass by becoming smaller. As mass increases, gravity forces the electrons towards speeds where special relativity matters. Their motion approaches the regime where adding momentum does not increase their ability to resist gravity in quite the same way. The detailed mathematics belongs to the later boundary, but the physical meaning can be felt here. The Pauli exclusion principle does not fail. The electrons still obey it. What changes is the effectiveness of the pressure it produces under extreme compression. The rule remains absolute, but the star's balance is not unlimited. A white dwarf can be supported only while its mass stays below the point where this quantum pressure can answer gravity strongly enough. This gives the Pauli barrier a quiet, dramatic shape. It is immensely strong enough to stop a stellar core from falling inward, yet it is not infinite. It can hold a remnant of ordinary stellar evolution, but not every possible remnant. It can preserve the exposed core of a low-mass star, but not the core of a far more massive one. It can make a dead star stable, but only inside a boundary written by mass, composition, and relativistic motion. The white dwarf therefore rests on both certainty and limitation. The certainty is that no two identical electrons may share the same complete quantum state. The limitation is that a star can become so heavy, so compressed, and so relativistic that the pressure arising from that rule no longer keeps collapse in the white dwarf form. For now, the important movement is inward rather than catastrophic. The faint remnant remains because its electrons occupy an invisible ladder of states, each step filled according to a rule that never needed the star to shine. The light can fade, the outer atmosphere can settle, and the surface can cool through ages too long for ordinary language to hold comfortably. Beneath that fading surface, the electron sea keeps its order. The dead star is balanced by exclusion, and the next mystery is how that balance changes when the whole remnant is treated as a star-sized quantum box. A white dwarf can be pictured, only imperfectly, as a quantum box built on the scale of a planet and filled with the mass of a star. The image is useful as long as it is treated gently. There are no hard walls in the ordinary sense, no polished boundary where electrons bounce like balls in a container. The confinement is gravitational. The star's own mass presses its matter inward, and the electrons, spread through the interior, are held in a volume far smaller than ordinary atomic matter would prefer. In that confinement, their allowed states are not arbitrary. They form a vast ladder of possible momenta, and the lower steps fill first. Once those states are occupied, the remaining electrons are forced higher. The white dwarf is therefore not quiet inside because nothing moves. It is quiet in appearance while its electrons occupy a dense distribution of motion, shaped by the rule that none may share the same complete state. The remnant stillness is a surface impression. Beneath it is an invisible ordering, imposed not by chemistry, not by heat alone, but by quantum confinement acting across the entire star. This is where the smallness of the electron meets the largeness of astronomy. A single atom is already a kind of quantum structure, with electrons allowed only certain arrangements around the nucleus. In a white dwarf, individual atoms have lost their old borders, and the relevant structure is expanded. The electrons are described less as residents of separate atoms, and more as a collective population filling the remnant. The nuclei remain heavier centers, positive charges arranged in a dense background. But the electrons supply the pressure that keeps the whole object from shrinking further. Their states extend through the matter, and the star behaves as though the interior volume itself has become the arena in which the quantum rule is enforced. To compress the white dwarf is to shrink that arena. Shrinking it does not simply place the same electrons closer together in a passive way. It changes the states available to them, and it forces the typical momenta upward. This is why greater compression creates greater resistance. Gravity tries to reduce the space. Quantum mechanics answers by making confinement more costly. The idea can be approached through a calmer version of a familiar principle from waves. A wave confined to a smaller region cannot have just any shape, it must fit. Shorter allowed wavelengths correspond to higher momenta, electrons, being quantum objects, carry wave-like behavior, and when their available space is narrowed, their possible states shift accordingly. In the dense interior, with enormous numbers of electrons and only limited room, this wave-like restriction becomes a pressure. The electrons are not pushing because they are angry or crowded in a human sense. They resist compression because the set of allowed quantum arrangements demands it. If the star is squeezed smaller, the electron distribution must include higher momenta, and that raises the pressure opposing gravity. The white dwarf becomes a physical compromise. Gravity sets the confinement, and the filled electron states set the response. This compromise is stable only because both sides adjust. If the remnant was slightly compressed, degeneracy pressure would rise. If it was slightly expanded, that pressure would ease. The star settles at the radius, where the two tendencies balance. This gives the white dwarf a strange kind of mechanical serenity. It is not held up by burning, so it does not need a constant central engine. It is not held up by rigid material strength, so it does not depend on the survival of ordinary solids. It is held up by a pressure that belongs to the electron sea as a whole. The object is self-gravitating, meaning its own gravity defines the problem, and quantum degenerate, meaning the occupancy of electron states defines the answer. That combination creates an equilibrium unlike anything encountered in daily life. The white dwarf can cool without losing the main basis of its support, yet it cannot ignore gravity. It is stable because gravity and exclusion have reached a truce. The truce becomes more unusual when mass is added. In an ordinary object, adding material often makes something larger. A pile grows. A planet becomes wider as it gathers more matter, at least until compression complicates the relationship. A white dwarf follows a more counterintuitive path. Adding mass strengthens gravity, and the stronger gravity confines the electrons into a smaller volume. A smaller volume means higher electron momenta, and therefore greater degeneracy pressure. The remnant answers the added weight by becoming denser and, in many cases, smaller. The star-sized quantum box tightens as the mass increases. This is not a decorative curiosity. It is the visible sign of the internal rule. The radius is not chosen by ordinary stiffness. It is selected by the balance between gravitational compression and the pressure produced by filled quantum states. More mass deepens the gravitational demand, and the electrons must move into higher momentum states to respond. The whole remnant shrinks into a new equilibrium. This inversion gives white dwarfs their distinctive place among compact objects. They are not as extreme as neutron stars, where matter is crushed beyond the white dwarf state and neutrons dominate the support. They are far denser than planets, where ordinary atomic structure still plays the central role. They occupy the middle territory, where electrons remain the resisting population, and nuclei remain separate enough that the object has not become nuclear matter. Inside that middle territory, the quantum box picture helps explain how a star can be both small and stable. The electrons cannot all settle into low-motion states. Because those states are already filled, they cannot all attach themselves neatly to individual atoms, because the atoms have been pressed into overlap. They cannot support an unlimited mass, because the pressure they generate changes as their momenta approach relativistic conditions. But within the allowed range, they provide a remarkably durable support. Their collective behavior turns a stellar corpse into a long-lived remnant. The interior is also not perfectly uniform. Density is highest toward the center, where gravity presses most strongly, and lower toward the outer layers. The composition can vary with depth. Thin surface layers may contain hydrogen or helium. While the main interior of many white dwarfs is dominated by carbon and oxygen, as cooling proceeds, the ions in the core may begin to crystallize, settling into more ordered arrangements. Yet the central idea of confinement still remains, wherever the electrons are degenerate. Their allowed states and momenta shape the pressure. Local conditions differ from layer to layer, but the whole star is governed by the same broad relationship between density and electron support. A white dwarf is not a simple box with uniform contents. It is a gravitationally layered quantum system, with pressure changing inward, temperature changing outward, and matter passing through states that ordinary language can only approximate. The box image gives an entrance, but the real object is subtler. This subtlety matters when light is used to study the remnant. Telescopes do not directly watch electrons fill quantum states. They measure brightness, colour, spectral lines, mass through orbital motion or gravitational effects, and radius through models and observations. From those outside clues, the interior equation of state is inferred. An equation of state is the relationship between pressure, density, temperature, and composition for white dwarfs. That relationship reveals the importance of degeneracy. If white dwarfs were supported by ordinary thermal pressure, their sizes and cooling behaviour would follow a different pattern. If their matter behaved like ordinary rock or metal, the densities would be impossible. The observed mass and radius of white dwarfs point instead toward the pressure of degenerate electrons. The faint object becomes evidence for the deep rule, not because the rule can be seen directly, but because no ordinary support gives the right structure. The star, measured from far away, carries the signature of its hidden confinement. There is a quiet elegance in that. A white dwarf does not need to be spectacular to be profound. It can sit in a catalogue as a faint source with a measured temperature and gravity. Yet behind those numbers is a structure in which the whole volume participates in a quantum arrangement. The remnant is not merely small, it is small for a reason. It is not merely dense. It is dense in a way that reveals the ordering of identical particles. It is not merely cooling, it is cooling while remaining supported by pressure that does not require the heat being lost. The star-sized quantum box is therefore not a metaphor for confinement alone. It is a way of seeing how the death of a star exposes rules that were always present, but usually hidden beneath the gentler architecture of atoms. Gravity has stripped away much of that architecture, and in doing so it has made the exclusion principle visible at astronomical scale. The next mystery follows naturally from this tightening. If adding mass makes the white dwarf smaller, then scale itself has been inverted. The more the remnant weighs, the more severe the confinement becomes, and the more deeply its electrons are driven into high momentum states. That inverted relationship cannot continue forever, but before the boundary appears, it reveals one of the strangest features of the white dwarfs in this kind of star. Heaviness does not expand the object into grandeur. It draws the object inward, toward a denser and more delicate balance. The most surprising thing about a heavier white dwarf is not how much mass it contains, but how little space it is allowed to take. In ordinary experience, added mass seems to bring added size. A larger stone weighs more than a smaller stone. A larger planet usually has more material spread across a wider sphere, even though gravity compresses its interior. White dwarfs do not follow that familiar intuition. For them, the path of greater mass leads inward. A more massive white dwarf is generally smaller than a less massive one, because the additional gravity presses the electron sea into a tighter quantum arrangement. The object answers extra weight not by swelling, but by increasing its density. This inversion is one of the clearest signs that the remnant is not supported by ordinary material strength. It is supported by degeneracy pressure, and that pressure rises only after the electrons are confined more severely. The white dwarf becomes a demonstration that size is not a simple measure of substance. It is a measure of balance, and in this balance, gravity and quantum exclusion negotiate the radius together. The reason begins with self-gravity. Every part of the white dwarf pulls on every other part, and as mass increases, the inward pull becomes stronger throughout the remnant. Stronger gravity demands a stronger response. In a normal gas, that response might come from higher temperature. In a white dwarf, the main response comes from pushing electrons into higher momentum states. The more mass the star contains, the more tightly its electrons must be packed, and the smaller the volume must become before electron degeneracy pressure rises enough to halt further contraction. The star does not shrink because the quantum support has weakened. It shrinks because shrinking is the way the support strengthens. The denser arrangement gives the electrons the momentum needed to resist the deeper gravitational well. A less massive white dwarf can be larger because it does not need as much degeneracy pressure to balance its own gravity. A more massive one must draw itself inward until the pressure becomes fierce enough to match the added load. This produces the unusual mass and radius relationship that sets white dwarfs apart from ordinary worlds. The relationship is not a decorative detail. It is a structural law. If white dwarfs were planets made of exotic solid material, more mass would not naturally lead to this specific pattern. If they were still supported mainly by heat, cooling would alter their radii in a way that does not match the long stability observed. Instead, their sizes point back to the hidden electron sea. Observations of white dwarfs in binary systems, where mass can be inferred from orbital motion, help reveal this connection. Measurements of surface gravity, temperature, luminosity, and distance allow astronomers to estimate radius. When the pieces are combined, the pattern agrees with the prediction that degenerate matter behaves unlike ordinary matter. The star is not merely compressed, it is compressed according to a rule. A white dwarf can hold a mass comparable to the Sun inside a sphere roughly comparable to Earth, yet a slightly heavier white dwarf can be smaller still. The visible surface becomes the outer sign of an invisible equation of state, a relationship between pressure and density written by quantum mechanics. There is a calm strangeness in this. A white dwarf's radius is not determined by a surface crust resisting like rock. It is not determined by a flame pushing outward from the center. It is determined by the density required for electron pressure to counter gravity. The star has to find the size at which those two tendencies meet. Too large, and degeneracy pressure is too weak for the mass. Gravity pulls the matter inward. Too small, and the electron pressure rises strongly, pushing back against further compression. The stable radius lies between those directions, and that radius moves downward as mass rises. In this way, the white dwarf's own weight chooses its compactness. It settles into a smaller shape because only a smaller shape can supply the necessary quantum resistance. The remnant does not have preferences. Of course, it follows the mathematics of matter under pressure. But the effect has an almost architectural clarity the heavier the roof. The deeper the foundation must be driven. That analogy can only go so far, because white dwarfs are not built from rigid supports. Their interiors are fluid in the broad physical sense, able to readjust under pressure, layered by density and composition rather than held in place by beams or stones. Yet the idea of load and response remains useful. Add mass to a white dwarf, perhaps through accretion from a companion star, and the remnant is forced toward a new equilibrium. Its gravity increases, its radius tends to decrease, its central density rises. The electrons become more energetic in their allowed states. This is not a gentle cosmetic change. It moves the star closer to the region where special relativity and the ultimate mass boundary begin to matter. The mass and radius relationship is therefore not only a curiosity about size, it is a warning built into structure. The shrinking of a more massive white dwarf shows that the remnant is approaching harsher conditions, even if its surface still appears as a modest point of light. the surface gravity changes with this compression. A smaller and heavier white dwarf has an especially intense gravitational field at its surface. Atoms in its atmosphere are pressed into thin layers. Heavy elements settle rapidly downward unless they are replaced by fresh debris from outside. Spectral lines can be broadened by pressure and shifted by gravity. Light climbing away from the surface loses a small amount of energy, producing a gravitational redshift that can be measured in favourable cases. These observational details matter because they let distant astronomers test the hidden structure. No instrument descends into the core, no sample is taken from the electron sea. The remnant is read from the outside, and its compactness leaves marks on the light that escapes. A more massive white dwarf does not simply hide its extra weight. It writes that weight into surface gravity, density, and the relation between brightness and radius. The inward trend also changes how the remnant ages. A white dwarf's cooling is shaped by its mass, composition, atmosphere, and internal structure. More massive white dwarfs have smaller radiating surfaces, which affects how they lose heat. But they also tend to have different internal densities and crystallization histories. The densest interiors can begin crystallizing at different stages, releasing heat and changing the pace of cooling. Some massive white dwarfs may have oxygen and neon-rich interiors, rather than the more common carbon and oxygen mixture, depending on the evolution of the parent star. These differences are quiet, but they matter over long spans. The heavy remnant is not merely the same object made smaller, its internal conditions may belong to a different history. Its parent star may have lived a shorter, brighter life before reaching the white dwarf stage. Its later cooling may carry signatures of composition and density that separate it from lighter members of the same class. In a population of white dwarfs, mass therefore becomes a record, not just a number. It points backward to stellar evolution and inward to the current state of degenerate matter. Yet the inversion of size and mass also creates a conceptual boundary around imagination. It is tempting to think that if gravity can always be answered by making the star smaller, then the process can continue without end. More mass, smaller radius, stronger electron pressure, and a new equilibrium. For a time, within the white dwarf regime, that is roughly the pattern. But nature does not allow the sequence to extend forever. As the white dwarf becomes more massive, the electrons are forced into higher momentum states. Their speeds approach a domain where ordinary, non-relativistic approximations no longer describe them well. The pressure still arises from exclusion, but the way it increases with density changes. The balance becomes more delicate. The same shrinking that strengthens support also moves the star closer to the condition where that support cannot grow fast enough to meet gravity's demand. The mass and radius relationship therefore carries its own limit hidden inside it. The path inward is not an endless solution. It is a road toward a threshold. This gives the white dwarf a restrained kind of tension. A lighter remnant can be broad by white dwarf standards, faintly cooling across immense time, stable far from danger. A heavier one is smaller, denser, and closer to the edge where its electrons must behave relativistically. Both may appear as small points through a telescope. Both may glow with old heat rather than fresh fusion. But their internal futures not identical. The lighter one has more room in the balance. The heavier one carries less margin. Its smallness is not weakness. It is the visible requirement of survival under greater gravity. Still, that survival is conditional. Add enough mass, and the very mechanism that allowed the star to shrink into stability begins to reveal its ceiling. The white dwarf is not a simple object becoming more compact at will. It is a quantum equilibrium being driven toward the limits of its own support. In the calm geometry of its radius, the next problem is already present. Heaviness draws the remnant inward. An inward motion raises the electron momenta until speed itself becomes part of the story. Special relativity enters the white dwarf quietly, not as a dramatic change in appearance, but as a correction that becomes unavoidable inside the densest part of the remnant. The electrons that support the star are not sitting still. They occupy momentum states forced upon them by confinement, and as the white dwarf grows more massive, those states reach higher and higher values. In a lighter white dwarf, many of the electrons can be described well enough by the older, more familiar relationship between momentum and energy. Squeeze the star more tightly, and that description begins to fail. The electrons are driven towards speeds that make relativity matter, not because the whole star is racing through space, but because the particles inside it are being forced into extreme motion by the pressure of gravity. The surface may still look faint and calm. The object may still be small, pale, and cooling. Yet within the electron sea, the calculation of support has changed. Motion near the relativistic regime alters how pressure grows with density, and that alteration is one of the reasons a white dwarf cannot support unlimited mass. The need for special relativity comes from the nature of electron degeneracy pressure itself. When electrons are crowded into a smaller volume, the Pauli exclusion principle prevents them from all occupying the lowest available states. They must fill higher momentum states, and the most energetic among them define an important scale inside the star. In a less compressed remnant, increasing density pushes the electrons into higher momenta, and the resulting pressure rises strongly enough to create a stable balance against gravity. But as momenta become extreme, the relationship between energy, momentum, and speed no longer follows the simple pattern of everyday mechanics. An electron cannot accelerate past the speed of light. As it is forced into higher momentum states, its energy continues to increase. But its speed approaches a limit. That matters because degeneracy pressure depends on the way the electron population responds to confinement. Relativity does not remove the exclusion principle. It changes the character of the pressure produced by the excluded states. The white dwarf remains quantum supported, but the support becomes less forgiving as the electrons become increasingly relativistic. This is a subtle point, and it is easy to mistake it for a failure of the quantum rule. The Pauli exclusion principle does not weaken under pressure. Electrons still cannot share the same complete state. They still fill the available states in the only way identical fermions can. What changes is how effective the resulting pressure becomes at opposing gravity when the electrons are already moving near their relativistic limit. In the non-relativistic case, compressing the electron sea raises pressure in a way that can answer additional mass by making the star smaller. The white dwarf shrinks. Density rises, and the stronger degeneracy pressure restores balance. In the relativistic case, the pressure still rises with density, but not steeply enough to keep pace with gravity forever. The star is being asked to support more mass with a pressure law that has softened in its response. The remnant can still exist below the critical boundary, but the old pattern of shrinkage and renewed support is approaching its end. This is why the more massive white dwarf feels like a quiet object with a hidden urgency. Nothing about its surface has to announce the change. It may simply appear as a compact source with high surface gravity, strong spectral broadening, and a radius smaller than that of a lighter cousin. Yet its interior electrons are occupying states that carry the imprint of special relativity. The object is no longer just a dense remnant supported by quantum exclusion. It is a dense remnant in which exclusion and relativity are working together to define the edge of stability. The distinction matters because white dwarfs are not dense enough to require general relativity in the same way black holes or neutron stars do. Their gravity is strong, but not usually strong enough for curved spacetime to dominate the structure at the level needed for the basic mass limit. The essential relativistic correction belongs instead to the electrons themselves. It is special relativity inside the matter, not primarily general relativity around the star, that reshapes the support. The result is a beautiful layering of physics. Gravity supplies the confinement, quantum mechanics supplies the exclusion. Special relativity changes the energy and pressure of the confined electrons as their momenta become extreme. Each piece matters at a different scale, and the white dwarf exists where they meet. It is not necessary for the remnant to become a black hole before relativity has consequences. Relativity is already present in the interior, long before space-time curvature becomes the main story. The dead star has become a laboratory for a quieter kind of extreme physics, where the limit is approached through particle motion, rather than through a visible horizon. The electrons are not seen directly, but their behavior determines the mass and radius relationship that telescopes can test. A faint point of light, measured carefully enough, becomes evidence that the universe respects the same speed limit inside a cooling stellar core as it does everywhere else. This connection between hidden motion and visible structure is one reason white dwarfs became so important in theoretical astronomy. The mass limit was not guessed from appearance alone. It emerged from combining the physics of degenerate electrons with the relativistic behavior required at high momentum. Without special relativity, the calculation gives a different impression of how much mass electron degeneracy pressure can support. With it, the sequence of stable white dwarfs bends toward a maximum. As mass rises, radius falls. As radius falls, density rises. As density rises, the electron momenta become more extreme. Eventually, the pressure response enters the relativistic regime so deeply that adding more mass no longer leads to a new stable white dwarf. The star is being driven toward a mathematical and physical ceiling. The surface remains a cooling atmosphere above compressed matter, but the future of the object is being decided by how the electron sea carries momentum. The calmness of the remnant makes this boundary more striking. In many astronomical settings, limits are announced through explosions, jets, disks, or violent collapse. Here the first sign is conceptual. The equation of state changes its slope. The way pressure depends on density becomes insufficient for endless support. A heavier white dwarf does not simply become a stronger version of itself. It becomes a more constrained one. Its shrinking radius is not merely an adaptation. It is a movement toward a point beyond which adaptation fails. This creates a kind of quiet suspense inside the physics, not the suspense of sudden disaster, but the suspense of a balance that can be written only up to a final mass. The white dwarf can remain stable for immense spans of time if left alone below that boundary. But if a companion star feeds it material, or if two white dwarfs merge, the remnant may be pushed toward conditions where stability has no white dwarf solution left. Special relativity is part of why that happens. It turns the strengthening of pressure into a support with a ceiling. The electrons still obey exclusion, but their relativistic motion prevents that obedience from saving the star indefinitely. There is also a deeper lesson in the way relativity enters without spectacle. The white dwarf does not have to be moving across the galaxy at extreme speed for relativistic physics to matter. Its internal particles are enough. The object's stillness on the sky conceals motion imposed by confinement. It shows that calm astronomical appearances can hide severe physical conditions, and that a star may seem least active precisely when its matter is most revealing. The remnant is cooling, but the electrons that support it carry enormous momentum. The surface fades, but the interior remains governed by laws that are far from gentle in their implications. A white dwarf is therefore not only a relic of stellar burning, it is a place where the speed limit of the universe shapes the architecture of a dead star. This relativistic edge narrows the story toward the next boundary. Gravity has been held back by quantum exclusion. Compression has been answered by higher electron momenta. Added mass has been answered by smaller radius and stronger degeneracy pressure. But once the electrons become sufficiently relativistic, the sequence can no longer be trusted to continue. The remnant approaches a final permitted mass, a value that marks the end of a white dwarf stability under electron degeneracy pressure. It is not a wall that can be touched, and it is not a surface inside the star. It is a boundary in the relationship between mass, gravity, and quantum matter. Beyond it, the white dwarf state cannot remain the same. The quiet edge of relativity has prepared the way for the Chandrasekhar boundary, where the fate of the compact remnant stops being a question of cooling and becomes a question of whether electron pressure can preserve the star at all. The Chandrasekhar boundary is not a surface waiting inside the white dwarf, and it is not a visible ring around the remnant. It is a limit written into the balance between gravity and electron degeneracy pressure. Below that limit, a white dwarf can find a stable size, small enough for the compressed electrons to provide the necessary resistance, yet not so massive that gravity overwhelms the available support. Above it, the old arrangement no longer has a white dwarf solution. The remnant cannot simply become a smaller and denser version of itself forever, because the pressure that once strengthened through compression has reached the point where its relativistic behavior can no longer keep pace. The name belongs to Subrahmanyan Chandrasekhar, whose early work showed that the physics of degenerate electrons, once special relativity is included, leads toward a maximum mass for stable white dwarfs. The value is often given as about 1.4 times the mass of the Sun. Though the exact number depends on composition and details of the stellar material, its meaning is larger than the number itself. It marks the place where a quiet stellar ember stops being able to remain what it has been. To understand the boundary, the earlier pieces have to settle together. Gravity compresses the remnant. The Pauli exclusion principle prevents the electrons from all occupying the same lowest quantum state. The electrons therefore fill higher and higher momentum states, producing degeneracy pressure. For lighter white dwarfs, this pressure rises strongly as the object becomes denser, allowing a stable balance at a particular radius. Add mass, and the radius decreases, the interior density rises, and the electron pressure rises with it. This behavior can make the sequence look self-correcting. More gravity creates more compression, and more compression creates more pressure. But special relativity changes the ending. When the electrons reach extremely high momenta, the pressure still exists, but its relationship to density no longer gives gravity the answer it demands. The remnant approaches a maximum mass, not because exclusion disappears, and not because the electrons stop obeying quantum rules, but because obeying those rules under relativistic conditions is no longer enough to support additional weight. The boundary is therefore a failure of balance, not a failure of law. This distinction keeps the idea from becoming too simple. The Chandrasekhar limit is sometimes described as though the white dwarf reaches a magic weight and instantly changes its nature. Real objects are more complicated. Rotation, magnetic fields, composition, temperature, accretion history, and binary interactions can affect how a particular system approaches instability. A white dwarf gaining matter from a companion does not necessarily move along a perfectly clean path. Material may pile on the surface, it may ignite in surface outbursts, it may be lost again. In some systems, the remnant may never reach the critical condition. In others, it may come close enough for carbon fusion, collapse, or explosion to become possible depending on the internal state and the way mass is added. The limit is still fundamental, but nature approaches fundamentals through messy histories. The calm number hides many possible paths toward it. What remains constant is the deeper lesson Electron degeneracy pressure can support a white dwarf only below a certain mass. Once the mass is too great, something else must happen. The Chandrasekhar boundary also changes how the white dwarf's future is imagined. A solitary white dwarf below the limit may simply cool for times beyond the present age of the universe. It can fade through successive thermal stages, crystallize internally, and eventually approach darkness without losing its basic identity. Its fate is governed mostly by heat loss and by slow changes in its material state. A white dwarf near the limit is different. It carries a structural vulnerability. Left undisturbed, it may still persist, but if it gains matter or merges with another compact remnant, it can be driven toward a point where cooling is no longer the main story. The question becomes whether the star can continue to hold itself up. A boundary that is invisible in a quiet object can become decisive when the environment changes. This is why white dwarfs in binary systems matter so deeply. Companionship can turn a cooling remnant into an unstable one by giving gravity more mass to work with. In some cases, the approach to the limit is connected with thermonuclear supernova, the powerful explosions used as distance markers across the universe. When a carbon and oxygen white dwarf is pushed into the right conditions, runaway fusion can tear it apart, releasing an enormous amount of energy. These events are not calm in themselves, yet their possibility arises from the same quiet balance described in the still white dwarf. The remnant that seems like an ember has a hidden threshold. Below it, matter cools. Near it, matter can become unstable. The Chandrasekhar boundary is therefore not only a theoretical mass, it is part of the reason some dead stars become cosmic beacons. It links the hidden physics of electrons to the large-scale measurement of galaxies, because certain white dwarf explosions help astronomers estimate distance and trace the expansion history of the universe. The faint corpse and the cosmic map are connected through the same limit. Still, the boundary should not be treated only through the violence it may permit. Its quieter significance is just as important. It reveals that stability in nature is often conditional. A white dwarf feels durable because its support does not depend on ongoing fusion, but durability is not infinity. The remnant survives because it lies within a permitted range. Its matter is arranged in a way gravity can compress but not freely defeat. It is a successful compromise, and the Chandrasekhar limit shows where the compromise ends. That ending is not imposed from outside. It emerges from the same physics that made the white dwarf possible in the first place. The support contains its own ceiling. The more mass the remnant contains, the more the electrons must occupy extreme states. The more extreme those states become, the more relativity reshapes the pressure. The very path that allows the star to resist collapse draws it closer to the point where resistance cannot grow adequately. The boundary is built into the solution. There is a kind of restraint in that idea. The universe does not need to announce the limit with a visible mark. It is present in the equations, in the measured masses of white dwarfs, in the absence of stable remnants far beyond the allowed range, and in the behavior of compact stars that cross into different fates. It is present whenever a white dwarf remains quietly below it, and whenever a system tries to push a remnant beyond it. The boundary separates two forms of aftermath. On one side is the long cooling of a stellar core, supported by degenerate electrons. On the other side is change collapse toward denser matter, runaway burning, or some more complex route depending on the star's history. The white dwarf state is therefore not the final answer to gravity in all cases. It is one answer available to certain masses. Beyond that range, gravity asks a harder question, and electrons alone cannot reply with the same success. This gives the Chandrasekhar boundary its calm power. It is a threshold of identity. Below it, the object may be called a white dwarf because its structure, support, and evolution belong to that class. Above it, the name begins to fail. The matter cannot remain arranged in the old way. Either nuclear reactions intervene, or collapse proceeds toward a state where protons and electrons are driven together, or the system is disrupted before a simple remnant can form. The boundary does not tell every detail of what follows, but it tells what cannot continue. The white dwarf cannot simply remain a white dwarf with more and more mass added to it. Its smallness has limits, its quantum support has limits, its quiet stability has limits. After all the slow cooling, all the faint light, all the delicate balance between gravity and exclusion, the remnant carries an upper edge that turns stillness into uncertainty. The next movement begins there, where the electron sea can no longer preserve the old form and the compressed stellar core is forced toward a different kind of matter. Neutron collapse begins where the white dwarf form can no longer preserve the separation between electrons and nuclei. Inside an ordinary white dwarf, the nuclei remain distinct, carrying most of the mass, while the electrons form the degenerate sea that supplies the main pressure against gravity. That arrangement is extreme, but it is still not the deepest form of compression matter can take. The protons inside the nuclei still exist as protons. The electrons still exist as electrons. Their identities remain separate even though ordinary atomic structure has been erased. But when gravity presses hard enough, the distinction becomes harder to maintain. The electron momenta rise. The central density climbs. The cost of keeping electrons as a separate population increases. At some point, the conditions favour a different transformation, in which electrons and protons are driven together and converted into neutrons, with neutrinos carrying energy away. The white dwarf has then moved toward the threshold of a more compact state, where electron degeneracy pressure is no longer the main support and matter begins to resemble the matter of a neutron star. This is not simply a matter of crushing empty space out of atoms. That older image is useful only at the beginning. In a white dwarf, the empty architecture of atoms has already been largely removed. The electrons are no longer orbiting their own nuclei in familiar shells. The interior is already a dense plasma of nuclei and shared electrons. The step toward neutron-rich matter is therefore not a further tightening of ordinary atoms, but a change in the identities of the particles that make up the support system. Electrons are absorbed by protons through a process often called electron capture. The result is a neutron and a neutrino. The neutrino interacts only weakly with matter and can escape, carrying away energy, with fewer free electrons available to provide pressure. The white dwarf's old support weakens. If the conditions are right, collapse accelerates. The remnant crosses from a state held up by electrons into a state where the resistance of neutrons, nuclear forces, and far more extreme densities become central. In this transition, the white dwarf does not merely become smaller, it becomes a different kind of object. The difference in scale is immense. White dwarfs are roughly planetary in size, though their masses are stellar. Neutron stars compress comparable or greater masses into a region more like the size of a city. That comparison is often repeated because it captures the severity of the transformation, but the deeper distinction is not size alone. A white dwarf contains nuclei immersed in electrons. A neutron star is dominated by neutrons packed at densities approaching those found inside atomic nuclei. Between these states lies a change in the form of matter itself. The support has passed from electron degeneracy pressure to neutron degeneracy pressure and nuclear interactions. The collapse has moved from the realm where electrons can still answer gravity into a realm where electrons have been largely removed from the role they once played. The white dwarf's boundary is therefore not only a limit of mass, it is a limit of composition, identity, and pressure. There are several possible ways a white dwarf can approach this edge, and the path matters. A solitary white dwarf born below the Chandrasekhar boundary can simply cool for immense spans of time. It has no obvious way to add enough mass to force collapse. But a white dwarf in a binary system may draw material from a companion, slowly increasing its mass. Two white dwarfs may spiral together and merge after losing orbital energy, especially through gravitational waves. In some cases, carbon fusion may ignite explosively before collapse into a neutron star can proceed, leading to a thermonuclear supernova that destroys the white dwarf. In other cases, especially for certain oxygen neon white dwarfs, electron captures may remove pressure support and trigger collapse toward a neutron star. The same broad boundary can therefore open into different endings. Some remnants are torn apart by runaway burning, others may be crushed inward into a denser corpse. The white dwarf state ends either way, but the manner of ending depends on the internal composition and the history that brought the remnant to instability. The oxygen neon path carries a particular quietness. Such white dwarfs are thought to form from stars near the upper end of the mass range that can still leave white dwarfs rather than undergoing ordinary core collapse as massive stars do. Their interiors are not the familiar carbon and oxygen mixture of many lower mass remnants. They contain heavier ashes from more advanced burning and under high density. Electron capture can occur on nuclei in a way that reduces the electron pressure supporting the star. Once enough pressure is lost, gravity no longer has the same resistance to answer it. Collapse can begin from within, not because the Pauli exclusion principle has been violated, but because the population of pressure-supporting electrons is being changed. Matter is finding a more favourable state under the conditions imposed by gravity. The support system is being dismantled by the very density it helped make possible. This gives the approach to neutron collapse a different feeling from ordinary mechanical failure. Nothing breaks like a beam. No shell cracks in the way a stone might crack. Instead, the equation of state changes because the particles themselves are transformed. The star's balance depends on how pressure responds to density, and electron capture changes that response. As electrons disappear into neutrons, the pressure that once grew from their degeneracy declines relative to the gravitational demand. Collapse can then proceed rapidly, and as matter compresses further, densities rise toward the point where neutrons become the dominant form. The remnant that emerges, if one remains after the event, belongs to a more extreme family of stellar corpses. Its gravity is stronger, its radius far smaller, and its internal physics closer to the nuclear realm. The white dwarf has been a bridge between ordinary matter and nuclear matter, and neutron collapse is the crossing beyond that bridge. Yet even here, the story remains anchored in continuity. The neutron star is not unrelated to the white dwarf. Both are compact remnants. Both exist because a form of degeneracy pressure resists gravity. Both show that the death of a star can expose quantum rules at astronomical scale. The difference is the particle carrying the support and the density at which the balance is reached. In a white dwarf, electrons provide the crucial pressure while nuclei remain separate. In a neutron star, neutrons become central, and the densities are so high that nuclear forces, superfluid states, crustal structure, and relativistic gravity all become important. The progression from white dwarf to neutron star is therefore not a simple ladder of smaller objects, but a sequence of physical regimes. Each regime has its own dominant support, its own limits, and its own way of answering gravity. White dwarfs occupy the electron-supported stage. Neutron stars occupy a deeper stage. Black holes wait beyond a still more severe failure of support, where no known pressure can prevent the formation of an event horizon. For the calm study of white dwarfs, neutron collapse matters because it reveals what the white dwarf is not: It is not the final possible density of stellar matter. It is not an unlimited refuge from gravity. It is not a permanent category for any remnant, regardless of mass. It is a stable arrangement available only while electrons remain numerous enough, degenerate enough, and effective enough to supply the needed pressure. Once that arrangement is undermined, the object must move into another outcome. This makes the white dwarf's long stillness more precise. Its stability is not vague endurance. It is a carefully bounded state in which gravity is strong but not victorious, and quantum pressure is powerful but not absolute. The existence of a neutron star beyond the boundary shows that nature has another answer to compression, but only at the cost of transforming matter more deeply. The old electron sea cannot carry the burden forever. The quietness of the transition in theory contrasts with the violence of the real event. If collapse occurs, it unfolds on timescales far shorter than the cooling life that preceded it. Neutrinos may stream outward. The remnant may release enormous gravitational energy. Surrounding material may be disrupted. A system that spent millions or billions of years as a faint cooling object can pass suddenly into a new compact state. Still, the physics leading there has been building all along in the relation between mass, density, and pressure. The final instability is not separate from the white dwarf structure. It is latent in the structure's limits. The same compression that makes the remnant stable below the boundary prepares the conditions that undo it above the boundary. This is the restrained lesson of neutron collapse. A white dwarf survives because electrons resist being crowded into identical states. But under enough pressure, the problem is no longer only where the electrons can go. It becomes whether they remain as free electrons at all. When protons and electrons are driven together, the remnant enters a different world of matter, one where the old white dwarf identity has been left behind. The passage toward neutron collapse therefore closes the central argument of support and opens the final, slower vision of cooling. Most white dwarfs will never make that crossing. They will remain below the edge, not collapsing, not reigniting, not becoming neutron stars, but fading with almost unimaginable patience into the dark future that waits for every stellar ember left undisturbed. The longest future of a white dwarf is not collapse, but cooling. Most of these remnants will never be pushed toward the Chandrasekhar boundary, never draw enough mass from a companion to ignite catastrophe, never merge into a new unstable object, and never cross into neutron collapse. They will simply remain. Their outer layers will thin into faint atmospheres of hydrogen or helium. Their interiors will continue to release stored heat through matter that has already outlived the bright life of the parent star. Their surfaces will darken by degrees too slow for any single civilization to witness from beginning to end. A white dwarf is born hot because it is the exposed core of a star, but it has no lasting furnace to keep that heat renewed. Its future is therefore a long descent through temperature, luminosity, and colour, a movement from bright remnant to dim ember, from visible star corpse to almost silent mass. The cooling is not an event, it is a migration through time, and it is so slow that the present universe has not yet had enough age to show the final state. The idea of a black dwarf belongs to that future. A black dwarf is what a white dwarf should become after it has radiated away nearly all of its remaining heat and no longer shines with visible light. No confirmed black dwarf should exist in the current universe, because even the oldest white dwarfs have not had sufficient time to cool so completely. This absence gives the concept a special stillness. It is not an undiscovered object waiting nearby, but a stage the cosmos has not yet grown old enough to make. Every white dwarf now observed is therefore still warm compared with its ultimate fate. Some may be ancient by galactic standards, dim and cool and difficult to detect, Yet they remain far from perfect darkness. Their light is thin, but it is still light. Their heat is low, but it is still heat. The universe has produced the embers, but not yet the cold ash. The path toward that darkness is shaped by more than simple radiating. The interior of a cooling white dwarf changes as temperature falls. In many remnants, the ions in the dense core can crystallize, arranging themselves into a more ordered pattern, while the electrons continue to form the degenerate sea that supplies pressure. Crystallization releases latent heat, a stored energy associated with the change of state, and that release can slow the cooling for a time. The remnant does not fade as a featureless object. It passes through internal transitions hidden beneath a thin, visible surface. The core may separate chemically as heavier elements sink and lighter ones rise within the crystallizing material. The pace of fading is therefore written by composition as well as age. A carbon and oxygen white dwarf cools differently from one with a heavier oxygen and neon interior. A hydrogen atmosphere insulates differently from a helium atmosphere. Magnetic fields, mass, and prior history all leave small signatures in the way heat escapes. Even the road to darkness has structure. This is why white dwarfs remain valuable long after their dramatic formation has ended. Their cooling sequence records time in star clusters, where many stars form together. The faintest white dwarfs help estimate the cluster's age, because their dimness marks how long the oldest remnants have been cooling. The method is careful rather than simple. Models must include the physics of dense matter, crystallization, atmospheres, and the mass distribution of the remnants. But the basic idea is elegant. A white dwarf cools because it cannot make significant new energy by ordinary fusion. Its fading light becomes a clock, not a clock with moving hands, but one written in temperature and luminosity. A single remnant carries its own thermal history. A population of remnants carries the history of a stellar system. The quiet point of light becomes a measure of deep time. Around some white dwarfs, the aftermath of planetary systems continues to disturb the calm. Asteroids, comets, moons, or fragments of former planets can be thrown into unstable orbits after the parent star loses mass. Some of that material may pass close enough to the white dwarf to be torn apart by tidal forces, forming dusty disks or raining heavy elements onto the surface. Because heavy elements sink rapidly in the intense gravity, their presence in a white dwarf atmosphere can point to recent accretion. This gives astronomers a way to study the chemistry of rocky material around dead stars. In a strange reversal, a white dwarf can reveal the composition of destroyed worlds more cleanly than the living star once did. The remnant becomes an archive not only of stellar death, but of planetary survival, disruption, and return. Even on the path to darkness, it may continue to gather traces of systems that once orbited in light. The future of these systems is quiet only in the larger sense. On shorter astronomical timescales, a white dwarf may experience surface accretion, atmospheric settling, pulsations, or debris interactions. But compared with the burning life of a star, its long destiny is still one of fading. As the galaxy ages and new star formation slows, more ordinary stars will pass through their final luminous stages and leave white dwarfs behind. The bright population of short-lived stars will vanish first. The long-lived red dwarfs will continue burning for immense spans before finally adding their own remnants to the growing collection. Far ahead, the universe may contain far more cold stellar remains than active sources of light. White dwarfs, and eventually black dwarfs, will become part of a dimmer cosmic inventory, one in which the evidence of former brightness is stored in compact masses drifting through darkening space. Yet this cooling is not the same as disappearance. A black dwarf, if time eventually makes one, would still have mass, gravity, composition, and history. It would no longer shine in the visible way that first gave white dwarfs their name, but it would remain a physical object shaped by the life of its parent star and by the quantum pressure that kept it from collapse. Its darkness would not erase the laws that held it together. Electron degeneracy pressure would still support it. Unless some later event disturbed it, the remnant would become harder to see, but not less real. This distinction matters because astronomy is often biased toward light. Objects announce themselves by shining, reflecting, absorbing, lensing, or moving other things. A cold black dwarf would be nearly silent to ordinary observation, yet it would still belong to the material memory of the universe. Darkness would mark not non-existence, but the exhaustion of thermal glow. The white dwarf therefore carries two kinds of time at once. One is the time behind it, the history of the star that formed it, the nuclear burning that made its interior elements, the shedding of outer layers, and the possible rearrangement of planets and debris. The other is the time ahead, the cooling through ages far longer than the star's active life, the slow crystallization, the dimming, and the eventual approach toward a state that has not yet appeared anywhere, because the cosmos is still too young. The remnant stands between a known past and an unseen future. Its present glow is a bridge, a visible trace of heat moving out of matter. As long as that glow remains, it allows measurement. When it finally fades beyond visibility, only gravity and consequence will speak for it. This is the final quiet mystery of white dwarfs. They are extreme without being loud. Their densities are enormous, yet most cool without spectacle. Their support depends on quantum rules, yet they appear as faint points in the sky. Their future extends beyond the present age of the universe. Yet their origin lies in the familiar life cycle of ordinary stars. They show that a stellar ending can become a long physical afterlife, not as a metaphor, but as a real sequence of states governed by gravity, thermodynamics, and quantum mechanics. A white dwarf is what remains when a star has stopped making light in the old way, and yet it continues to matter for a nearly unimaginable duration. It cools, records, resists, and waits. In its fading, the universe reveals a gentler form of endurance, one not based on renewal, but on the slow release of what has already been made. The silent mystery is not only that white dwarfs survive the death of stars, it is that they survive so quietly, holding stellar mass in planetary space, letting their light fall away while the deeper pressure remains, and carrying the memory of fire toward a darkness that has not yet had time to arrive. The white dwarf remains as a calm lesson in scale. A star can lose its outer layers, end its fusion, and surrender the bright pressure that once held it open, yet still not vanish into collapse. What remains is smaller, quieter, and stranger than the star that made it. Its glow is only stored heat leaving slowly, but beneath that fading light is a deeper steadiness, shaped by electrons, gravity, and the quiet rules of quantum matter. In that steadiness, the universe shows that endings are not always sudden. Some endings become long conditions, some become remnants that cool for ages while still carrying the imprint of everything that came before. The white dwarf holds the memory of burning without burning as it once did. It holds mass in a small space without becoming ordinary matter again. It holds silence without emptiness. Around it, planets may be gone, scattered, broken, or reduced to traces in a thin atmosphere. Inside it, nuclei may settle and crystallize while electrons continue their hidden resistance. Far ahead, when its last visible warmth has faded, it may become dark enough to escape easy notice, but not meaningless, its gravity will remain, its history will remain. Its existence will still be a record of a star that once shone, changed, released itself, and left behind a compact ember for the deep future. In the end, white dwarfs do not need grandeur to feel profound. They are quiet because their story has moved below the surface into slow cooling and lasting structure. They remind the mind that even after brightness has passed, form can remain, balance can remain, and the universe can continue its patient work in near silence.